to chapter 8.2. Now in this section we are going to study systems of differential equation with two dependent variables. Specifically we are going to consider homogeneous first order linear system of differential equations with constant coefficients. A typical form of a system would be something like this. So we have two dependent variables x1 and x2. Then x1 dot equals to ax1 plus bx2 and x2 dot equals to cx1 plus dx2. Here a, b, c and d are constants. Now as you know, the matrix form of this differential equation is the following. So we have the derivative of a vector x. This is our vector x and it contains two elements x1 and x2 equals to the coefficient matrix A and then the vector x. So here we have the derivative of the solution vector. Now in this compact form, this differential equation can be written like this: vector x prime equals to a times x. As an example, the matrix form of this differential equation is, okay, now let's say our vector x contains two elements x1 and x2. Then x prime is this, the vector x1 x2 prime. The coefficient matrix A has the elements 1 1 4 1 and then the vector x with elements x1 and x2. Great. So now in this section our main goal is to solve a 2x2 system. So basically we have two dependent variables with constant coefficients. Okay, now if you recall the first part of the ODE, if we have a differential equation like this, let's consider a differential equation with one variable, something like with constant coefficient, then the candidate solution for this one was e a to the t. But now we have a system of differential equation that is in this form: vector x prime equals to a times vector x. So this should be a vector x. So then the trial solution that we are going to consider is very similar to this one, but now x should be a vector. So now let's consider a trial solution in this form. So e to the lambda t, here lambda is a scalar, but now ultimately somehow we want to get a vector. So let's multiply this scalar function e to the lambda t by vector v. So this is our trial solution. And here lambda is a scalar, v is a vector. And the dimension of this vector v is the same as the dimension of this vector x. In other words, if vector x is a 2x1 vector, then vector v is also a 2x1 vector. Okay, so this is our candidate solution. Now if this is a candidate solution, then let's substitute this candidate solution into the system of differential equation. Okay, first thing first, we want to calculate x prime. So if x equals to v e to the lambda t, here lambda is a constant, vector v is a constant vector. So if we differentiate this one with respect to the t variable, you should get lambda v e to the lambda t. So basically this is a constant, and then if you differentiate e to the lambda t, you will get lambda e to the lambda t. Okay, now let's substitute these two quantities into the differential equation. If you do that, you will get lambda v e to the lambda t equals to a times v e to the lambda t. Great. So now we know that e to the lambda t does not equals to 0. So what we could do is we could divide both sides by e to the lambda t, and then we get lambda v equals to a to the v. Excellent. So this means if our v and lambda satisfy this equation, then we have our solution. Okay, now here we need to find two things. We need to find the lambda value and we need to find the v value, the vector v. Okay, so how do we find these two quantities? Okay, so let's rearrange this. So we have lambda v equals to a times v. Now for a given system, we know what a is. Okay, but now we want to find lambda and v. Okay, so what I'm going to do is I'm going to take this quantity lambda v quantity to the other side. So then we have 0 equals to a times v minus lambda times vector v, and we can factor out vector v. This should be a vector, because we are subtracting two vector quantities, then we should get the 0 vector. But now if we factor out vector v, you will get a minus, but lambda is a scalar, a is a matrix, so we should attach the identity matrix to lambda. Okay, so basically we rearrange this equation into this, and you must remember this: we are looking for non-zero values for vector v. If it is 0, then that's the trivial solution. Now this is where we used a theorem from linear algebra. This theorem says if we are looking for the non-zero values for vector v, then the determinant of a minus lambda I should be 0. And we have a special name for this equation, and this is the characteristic equation. So using this equation, what we could do is we can find the lambda value. After that, for each lambda, we go and solve this equation for v, and then we can find the corresponding corresponding v values. And we have a special name for these two quantities. In linear algebra, we say that this lambda is an eigenvalue and vector v is an eigenvector. And to conclude this video, I'm going to state this theorem. So the eigenvalue solution of x prime equals to ax is given by the eigenvalues and eigenvectors of this matrix A, and then vector v is the associated eigenvector for lambda. Once you have your lambda value and this eigenvector v, we can get the corresponding solution using this equation, where x equals to v times e to the lambda t, which is a non-trivial solution. Now throughout this lecture, if I use the letter V without an arrow or with an arrow, that is an eigenvector, and if I use a capital X or big X like this, it is also a vector. Sometimes I may write the arrowhead, or sometimes I may not. Okay, with this I finish the first video of this section, and next we are going to consider few examples.